Hi guys. In the ongoing effort to try to simplify things and make it easier to understand, I've been reworking these EKG slides. So, um, it's very similar, just broken it up into a few slides. So, we say, look, here's our characteristic shape. You probably should add in, excuse me, again, the pictures of the heart with its auricle atriums and ventricles, and match up, and the nodes, remember, AV node, etc. And there's the different stages, and you can point out, well, this is that stage, this is this stage, or here, all these different things there. That's important. And then you say, look, when these nerves and muscles do their thing, whenever a nerve signal or muscle contraction, there's large numbers of ions move. And it's the calcium 1 plus, calcium 2 plus, the potassium, there's among others. And anytime ions move, they're charged particles. Anytime it moves and stops or moves and changes directions, you create a pulse. And so not only do you say, okay, there's a pulse that travels in time, it travels away from the heart. So you get this moving pulse of voltage. And then these electrodes pick it up. And the time part comes in, because first let's see, what would come earlier in time. Good question. What comes first? The P wave? Well, each of these arrives. Yeah, this is earlier in time. That's later in time. So the P wave arrives, then all these different parts arrive, and the electrocardiogram just records the voltages. And this is where you say, well, heck, it is. Notice that the amplitude, the height of these things, is in millivolts. Then so first of all, as before, we had to find the characteristic shape, and this is what it looked like. This is what it looks like in reality. It's only millivolts. And then we had a new challenge, because when we did the data rate study, we noticed that there's this. It got messier and messier because of this background noise thing. Okay, so a nicer way to look at data rate, I just made these up, and so it looks better than what's in the lab manual. In fact, I'm going to add these to the lab manual. So I have some sine wave, and that's the black trace, and these are in no particular order. But if I sample, let's say the sine wave is 1 hertz. So if I sample at 2.5 hertz, or 2.5 times the signal frequency, you see that these orange lines are not really that great. And, we have the luxury of having a precise sine wave. So even if these blue points were to move back, slide a little bit over and back, yeah, you'd see a kind of symmetric pattern. And when you get to 4 times and 6 times, you'd say, well, those work out all right. But imagine that you've got this now shape like this. So when you move, if you're sampling, because you don't have control over what part of the waveform that sample is taken. So if you look here, this one with 10 points per wavelength, so this is 1 wavelength, 10 times the sampling, 10 times the frequency, then even if they move back and forth a little bit, the orange lines always stay like the original wave form. So basically, you need at least 10 times the frequency rate. So now we look at somebody's EKG, and you say a heart rate could be 60, and maybe it's at 90, it can be even more, but let's say for the sake of argument here, so 60 hertz is about 17 milliseconds, and in fact 90 hertz is less, right? So in fact I said 20 milliseconds, but we'll stick with that. So let's say there's 20 milliseconds between repeats. So that means then that the frequency is 50 hertz, right? Because 60 hertz. So that's a 50 hertz. So it's a little bit slow for a heart rate, but 20 milliseconds is just so easy to work with. So 10 times that to get 10 points. So if it's 20 milliseconds, then I want every 2 milliseconds, I want to take so that's 1/10. So 1 over 2 milliseconds equals 500 hertz. So we need to sample the electrocardiogram output at least 500 hertz. Okay, great. So now we have our procedure. We do a data rate study, and we notice that as we go up, well, first of all, we just say, look, we did the data rate plots and overlaid them, and we go from 50 to 100. We start seeing the characteristic shape a little bit, but then as we think, okay, we're going to go up to 250, and then we're going to go up to 500, and we're like, oh my God, it's a disaster. And the problem is that, and see, this is 4 seconds, just like those previous ones. There's all these tiny, tiny little wiggles. So that means is that every one of these, the black sine wave here, has added on to it these tiny wiggles. And worse still, the tiny wiggles, I have this set up at 100 millivolts. So these are a little bit bigger than the ones we actually observe. Well, I don't know. Let's take a look over here. So yeah, these wiggles are, so just like the, see, 1 millivolt, just like the plot we have in the lab manual. And these wiggles, right, they're on the order, and I didn't even show the negative end here. These are on the order also of 1 millivolt. So the wiggles are serious. They have a serious effect on the signal. But we thought, well, maybe we'll go to 250 hertz, and that might work. But we really want the 500 hertz. So yeah, the noise comes in, because I explained it a little differently. I did this window thing, and I think this is just easier to understand. All these tiny little wiggles. So just like in the moving average of the COVID, the number of cases, we realized that we've got to do a kind of averaging just like they do. And so we plotted the 500 hertz. We used the trend line with the moving average to decide how many averages we were going to make. And so 6, 8, or 10, and then now we're not going into details about exactly what it's doing, other than it makes it look nicer. And for us, the explanation is it just gets rid of all these tiny wiggles. It's sort of like what I was doing here. So in this case, this is frequency. This has a sampling of 2000 hertz. And now if I lower the sampling rate to 200, then I don't see as much noise there. So that's sort of it's the equivalent of doing a moving average of 10. So it knocks the noise way down, and in fact, that's exactly what we see. Gets rid of all the little wiggles. And for physics 1200, that's really all we need. So what I need to do is to play these few new slides to make them available as PowerPoints, so you can copy paste these diagrams as you like. All right, that's it.